So you have to very focus what we are doing. And also we have only 1 hour lecture today because we are going to have a quiz at the end of session. So let me read a definition of exact form, exact differential equation. Let fxy be a two-variable function. So this is a function on two variable. We have x and y both independent variable. Usually we have y as a dependent variable of x, but here we have a formula of x and y which both depends on x and y, but depends on this variable x and y. 자, 오늘은 LMS로 강의하는 게 아니라 유튜브로 강의를 하는데 댓글만 LMS에다가 쓰셔야 돼요. 질문이 있으면 LMS에다가 댓글로 그 채창 있죠? LMS 채창에다가 궁금한 거 있으면 다루시라고요. 유튜브는 아무나 들어오니까 지난번에 너무 더러워져서 네, 좀 잘 요약해 주셨네요. So first of all, let's define total differential of f. So total differential is of this form. So this df is called the differential of f, and df equals to the curly f curly x dx plus curly f curly y dy. It's called the total differential of f. So this formula, not the equation, the formula, this part formula is called the total differential of f. So this might be somewhat awkward to you because I used curly d instead of d. That's because I'm taking a partial derivative instead of derivative. Now, the function f is the function of two variables, so you can take either a derivative in terms of x or derivative in terms of y. When you take a derivative in terms of x, you consider y as a constant and take your function as if it's a one variable function of x. And when you take a derivative of y, you take x as a constant. So let me give example, an easy example of partial derivative. So if you have a function, let's say e to the minus x plus y. So this is a two variable function. This is not an implicit function. And if you take a partial derivative of x, this is also denoted by del f, del x. You take x as a variable and y as a constant. So by taking the derivative of exponential, you get the same exponential function, and also you take the derivative of the composite function here. So you're taking a derivative of minus x plus y. So you get minus 1. So you're not getting minus 1 plus y prime because y is not a derivative. Y is not a function of x. So basically this is minus e to the minus x plus y. And what about fy? This is simply e to the minus x plus y. So we consider the whole thing as a function of y. And then when you take the derivative of exponential, you get 1. Okay? So very simple way to take a partial derivative, and this does not tell you the exact definition of partial derivative because we are going to learn that in the next semester in multivariable calculus course. But for now, we're going to use the notion of partial derivative because the differential equation is, so you're going to write your differential equation in this form by separating dx and dy. Now, in this case, y is a function of x. Your y here in this differential equation is function of x, but the formula appears as a coefficient of dx and dy are two variable function of x and y. Okay, so we call this an exact differential equation if there exists a two variable function such that if you take x derivative, then it becomes a coefficient function of dx, and if you take a derivative of y, then it becomes a coefficient of dy. So basically, what happens is that if you have a function of two variables such that your equation, the differential equation, becomes a total differential of the function, then we call this differential equation an exact differential equation. And moreover, the solution to this differential equation is this equation, the two variable function f, x, and y equals to c. So this one is also considered as implicit equation of y. So that's why we're calling this as a solution, because we're expressing function y in terms of x. So at this point, it might be very confusing because you're not familiar with the partial derivative, or you're still not confused, still not comfortable with this implicit equation. So let me give an example here. So let's look at the example in the below, this example. So suppose that we have a differential equation of this form. Let me write in the blackboard. So we have y prime. So simply it's a derivative of x and a derivative of y in terms of x. And it's given by minus 2x plus 3y and 3x plus 2y. So this is a differential equation. And this is not one that you can solve by separation of variable, because these numerator and denominators are not solely a function of x or y. So you have to use the exact form of differential equation. So when I say, when I rewrite this in terms of dy and dx, I separate this y prime as a fraction of dy and dx. Consider that dx is an infinitesimal change of x and dy is infinitesimal change of y. And I switch the denominators to the opposite side, so I get minus of 2x plus 3y dx is equals to 3x plus 2y of dy. And then move this to the right hand side, I get 0 equals to 2x plus 3y dx plus 3x plus 2y dy. Okay? So in this case, we have mxy equals to 2x plus 3y as a coefficient of dx, and this part is nxy. Okay? So let's move back to the theorem in the slide. So if you have an exact differential equation, for example, if you have a function which partial derivative in terms of x becomes the coefficient of dx, and partial derivative of y equals to the coefficient of dy, then you can solve your differential equation. So the question is, how do we know that given differential equation is exact or not? So theorem tells you the condition, the if and only if condition, when the differential equation is exact. So this is when the coefficient of dx as two variable function has partial derivative of y equals to the partial derivative of coefficient function of dy. So you have to be consider this very carefully, because what we are trying to find is a function such that m is equals to the partial derivative in terms of x, and y as a partial derivative of some function in terms of y. But this equation tells you, if I plug in m equals to f of x, this tells you that del f of x del y is equals to del f of y del x, right? So you have a partial derivative, first order partial derivative, and then take another partial derivative with different variable. So what you get is the second order partial derivative on the left hand side, which gives fxy, so denoted by fxy. It means simply that you're taking partial derivative of x first and then take the partial derivative of y. And on the right hand side, you also get a second partial derivative, but the order of derivative is interchanged. You first take the partial derivative of y and then take the partial derivative of x. So whenever you have a function of x and y, it doesn't matter which order you take the partial derivative. If you want to get the second order partial derivative, it matters when you take it matters how many times you take the partial derivative for each coefficient, for each variables. But if the number of variables that you take the partial derivatives are equal, then the order doesn't change. The order doesn't matter. So in general, if you can have second order partial derivative fxx, you can take x again, partial derivative of x twice, and also you get fyy by taking partial derivative of y twice, but these are not equal, and these are not also equals to the partial derivative of fxy. However, you can change the order of partial derivative in here. So that's basically, this equation is basically telling you that any function will have the same partial derivative by changing of order of partial derivative. So let me go back to the example here. So let's check whether this is exact by theorem. So we have m, and let's take the partial derivative of y of m. And what we get is taking a derivative of 2x plus 3y by y by taking x as constant. So 2x disappears by taking derivative, and 3 survive. And this nx is taking partial derivative of 3x plus 2i by x, so it's 3. So they are equal. So we know that this equation is exact differential equation. Then we can solve the solution of differential equation. So finding a solution is just almost try and error, but once you know that this is exact, then this try and error method is not that hard, because we want to find a two-variable function f. We want to find f of xy such that if I take the partial derivative of x, then I get this m, 2x plus 3y. And also if I take partial derivative of y, then I get the second coefficient, 3x plus 2y. Now, let's start from this equation. Now, we have, suppose that we have some polynomial function and I take the partial derivative of x, I got this one. When I take the partial derivative, I take y as a constant. So I can imagine that my original function is the integral of 2x plus 3y considering y as a constant. So this 2x comes from x squared and 3y comes from 3xy. And there could be another coefficient. There could be another terms in terms of y, because if I had a y term, term that consists only y, then if by taking a partial derivative of x, that will be disappeared here. So I can imagine that there could be a term solely in terms of y. And let's compare that with this one. So if I had a function f of this form, and I got fy equals to 3x plus y by taking derivative of y, then this guy with this intermediate fact that if I take a derivative of y, this will disappear, x squared will disappear. I get 3x plus g prime y must be equals to 3x plus 2y, right? So gy could be 2y squared. And also you can put a constant here, but it's not really necessary because we want to find a two-variable function satisfying the total differential is given differential equation. So we have xy, fxy equals to x squared plus 3xy plus y squared as an example such that total differential df is equals to given differential equation 2x plus 3y dx plus 3x plus 2y dy. Okay. Now, what is the solution? Solution is not this function. Solution is an equation given by f equals to some constant 3xy plus y squared plus c. So c can be any constant. So this is a general solution of given differential equation. This is a general solution. Okay. You can check inversely why this implicit equation becomes a solution to the differential equation by taking derivative in terms of x, considering y is a function of x. However, you can also take, or you can simply take a differential here is 2x plus 3y plus 3xy squared plus 2yy prime equals to 0, and that becomes exactly the same differential equation here. Let's look at another example here. We have, as a second example, we have differential equation. We don't know yet whether this is exact differential equation or not. You have to check by this theorem. And also we want to find a particular solution satisfying this initial condition. So let's look at, let's do this one. So differential equation is 2xy dx plus y squared x squared dy equals to 0. And initial condition is y2 equals to 2. So this guy, 2xy, is m, and this guy is n. Let's take my and nx to check whether this is exact. So my is 2x and nx is also 2x, so they are equal. So this is the exact equation. So if you have an exact equation, we can find a function f satisfying fx fx equals to m and fy equals to n. Now start from this equation. What you get is fx must be equals to 2xy. That means my f is x squared y plus some y terms. And using this fact, if I take a derivative of y, I get fy equals to x squared plus y g squared y, g prime y, and that must be equals to y squared plus x squared. So I know that my gy must be 1 over 3 y cubed. So fxy equals to x squared y plus y, 1 over 3 y cube. Okay. So I don't have to put the constant term here because I only want to get a function satisfying the total differential is given differential equation. This is not a solution yet. This is simply says that a general solution to this differential equation is fy, which is x squared y plus y cubed over 3 equals to c. So this is general. This is the solution. So here, as I said, y is an implicit function of x. Okay. So simply y is given as an implicit formula in this situation. So, okay. I have to put a little bit further here. Okay. Okay. So we have an initial condition, which is y2 equals to 2. So I can determine my constant c because this equation must satisfy when x equals to 2 and y equals to 2. So 2 squared 2 plus 2 cubed over 3 must be equals to c, which is 8 plus 8 over 3. So this is 32 over 3, right? So the final solution, this is a general solution. We want to find a particular solution satisfying this initial condition. So final answer is x squared y plus y cubed over 3 equals to 32 over 3. So this is the solution, okay? So let me pause here and take questions. 자, 늦게 들어오신 분은 오늘은 댓글을 유튜브에서 달지 말고 LMS로 들어오셔서 그 온라인 수업 창 있죠? 그 안에 들어오셔서 그 세션 참가하신 다음에 그 안에서 이제 채창에다가 그 질문해 주세요. And X. Okay, so first question is nx is y squared plus x squared. So we're going to take a derivative in terms of x, right? So y is considered to be constant. So y squared disappears. And we're taking a derivative of x squared in terms of x, so get a 2x. And the second question, how do we get the general solution? So we have a function satisfying this formula, right? So then, by taking a total differential of f, we have df equals to the total differential of this guy, so square fx dx plus fy dy, and we set this f satisfying this condition, these two conditions. So this is exactly same as m dx plus n dy, where m and n are in of this formula. Now, if we set this equation, so f of xy equals to c, what's the d of the constant? So when you take a d of f or d of x at dy, that's the infinitesimal change of variable x, y, and f. So you can change your f by changing x and y. So df is measuring how much your function of two variable changes by the change of x and y. However, if you take the d of the constant's always the same. So there's no change of value, right? So we have d of c equals to 0. So when you take a total differential of this equation, the implicit equation, then this part, the total differential of this part is same as the given differential equation, m dx n dy. And the total differential of constant becomes 0. Okay? So that's exactly the differential equation we started from. So that's why we have a solution to this differential equation. Okay, so let's move on to the integrating factor here. Now, your given differential equation may not be exact. So what can we do if it's not exact differential equation? We can multiply some factor to the dx and dy, which doesn't change the equation at all, but only change the coefficient, and sometimes it becomes exact differential equation. So not always, but there is a case when we can make our given differential equation an exact differential equation. So such a factor is called the integrating factor. And we're going to talk about how to obtain such integrating factor. So suppose that we have exact differential equation by multiplying the integrating factor. So this part is becoming our new m, so let's call it m prime, and this part becomes our new n, so let's call it n prime. So if it's exact, then if and only if condition tells you that n prime dy and n prime dx is equal. So when you take a derivative of this multiple, you can use the product rule. First, take the partial derivative of the first factor, nu, and then take the second derivative of second factor. So that's the left-hand side of this equation. And also you can do the similar to the right-hand side. You get this one. So in general, these terms, the partial derivative terms, may not be 0. But if you have a situation when this term, so this one, or this one becomes 0, then you can find your integrating factor using separation of variable. Let me repeat that in the blackboard. So if this part is 0, the partial derivative of mu with x is 0, then what you get from the equation in the slide is mu del y m plus mu del m del y equals 2. So this factor is 0 times n plus nu times del n del x, right? So let's combine these two factors to the right-hand side. So we get del u del y m equals to del n del x minus del m del y mu. Now, we have a 0 when I take a derivative in terms of x. That means mu has no x factor. There's no x term in the formula of mu, which means that mu is a function of y only, right? So I can consider my mu as just single variable function in terms of y. So this becomes nothing but simple derivative of y, of mu in terms of y, and m. And also, this is, let's abbreviate the notation, nx minus my times mu. Then let's use the separation of variable. Use separation of variable. Let's take the entire part nu to the left hand side, and then take dy to the right hand side, and also m. So m and x minus my times dy. And then let's take the integration. On the left hand side we get ln of nu, and on the right hand side we get ln, just integration, the same integration, m and x minus my dy. So you have to be careful when you take an integral here, because this is the integration of function of y. Okay, so there is no x term here, because you see the y is a function of mu is a function of y. So when I put this m to the right hand side and put nu to the left hand side of this equation, so let's write it here. So mu d mu dy equals to nx minus my over m. This left hand side is a function of y, and therefore the right hand side, which is equal to the left hand side, must be also a function of y. So when I take the integration of this part, this is just simply a one variable integration of one variable function, and we don't know what this is going to be because we don't know exactly what n and m are. So let's leave it like this, and then the final nu will be e to the this integration nx minus my dy. So this will work because we started from the assumption that this is an exact differential equation. So if you take your integrating factor by taking an integration and taking the exponential, this will be the right factor that you have to use. And also you can start from the condition assumption that this del u del y equals to 0. In that case, you have a slight different formula. Let's summarize that in the slide as follow. So since only thing that we can check in practical situation is this the fraction of this form and this form. The bottom one is the one that we did in the blackboard. So this is when this mu x equals to 0, and this is when mu y equals to 0. So when mu y equals to 0, this will be the factor that equals to mu 1 over mu dx, and this is the factor equals to d mu dy. Okay. So if this term is equals to, it's just a function of x. So if this is a single variable function, then integrating factor is the exponential of this. And if this is a function of y, then integrating factor is this. Okay. So you have to be able to derive this theorem without memorizing any terminology here. But it's useful to just remember which type of formula should be a function of which variable. So let's solve some example here. So we have first. Let's solve the first one. Since it could be confusing, so just for now, let me rewrite that formula in the blackboard and then start the solution. So if my minus nx is a function of x, or nx minus my is function of y. Okay, so there are two things that we have to check, whether this is function of x or this is function of y. Okay, and then let's begin our this examples in the blackboard. Okay, so we have y x minus y square cosine y dy equals 0. So in this case, if you assume that we are given without any information to solve this differential equation, you have to check whether this is exact differential equation or not. So first of all, this m is y, and n is not x minus y squared. It has to contain minus 1 here. So we have minus x plus y squared cosine y as n. And my equals to 1, but nx equals to negative 1. So these are not equal. So this differential equation is not exact differential equation. So we have to look for integrating factor to make this as an exact differential equation. So let's check this one first. So when I take my minus nx over n, so I compute my already. So 1 minus, and nx is minus 1 over n. So n is minus x plus y squared cosine y. And this is not a function of x because there's y in the formula. So this cannot work. Let's look at the second one. We have nx minus my over m, which is equals to, denominator is y, and nx minus 1, and my is 1, so minus 1. So this is minus 2 over y. Now this is function of y. That's what we required here, right? So it is a function of y. So we can imagine that our integrating factor should be e to the minus 2 over y dy. Okay? So let's compute here. So this is e to the negative 2 ln y. Now this is indefinite integral. So you can imagine that you have to put the constant c in front, but we are finding a single integrating factor, not the complete family of integrating factor. So it doesn't matter whether you put a constant c or not, because when you multiply your integrating factor, multiplying constant doesn't change anything. So you can just leave it like this, just in this case. And if you keep computing, you get 1 over y squared. So this is a integrating factor. Let me just emphasize again. So no constant C is necessary because we only need one integrating factor. Okay. And then let's multiply this factor to the given equation. What we get is y 1 over y dx minus y square x minus cosine y dy. Let's put the negative inside. So okay, this is our new differential equation, but exactly the same as the original one because I just multiply the same factor on the left and right. But on the right, it's 0, so still 0. So let's make this as m and this factor as n. And you can easily check that my is now equals to nx. And let's try to solve this exact differential equation by finding two variable functions satisfying the condition that f of x equals to m and f of y equals to n. So first of all, if f of x equals to 1 over y, then f must be equals to x over y, right? Because that's what we get after taking derivative of x by taking y as a constant, and plus some factor of y. So when you take the derivative of y, again, you get x minus x over y squared plus g prime y, and that must be equals to n. So the first factor is already appeared here, so the g prime y must be cosine y. So gy must be sine y. So fxy equals to x over y plus sine y is one example that total differential is this exact differential equation. So what's the solution? This is not solution yet. Solution is x over y plus sine y plus, equals to c. C is a random constant. So this is the solution. You can check that this is a solution by just plug in your, by taking a derivative on both sides and check whether the solution, check whether the derivative satisfies this differential equation. Okay, let's look at the second equation, second solution, second example. We'll erase up to here. So second one is a linear differential equation, dx dy plus y equals to x. Now, it seems like you can solve this by separation of variable, but you can't, because if you take dy dx equals to x minus y, you cannot separate your x terms and y terms by multiplication. It's just integrated in one factor, right? So cannot solve by separation of variable. So you have to use the exact formula or integrating factor in that case. So let's make it into, try to make it into an exact differential equation. By taking dx, multiplying dx on both sides, we get dy plus y dx equals to x dx. And let's pull back x dx to the left-hand side, you get y minus x dx plus dy equals to 0. So in this case, this is m and this is 1 is n. So m is y minus x, and n is simply a constant n, because you can imagine that 1 is just not, 1 is hidden here. And let's try to compare the my and nx. My is 1, and nx is a derivative of constant, so it's 0. So these are not equal. So this is not exact. We have to find an integrating factor. Let's look at two formula. First, let's look at my minus nx over n, which is n is 1, so my is 1 and nx is 0. So we get 1. How about the other one? Before I make a conclusion here, let's try to see what happens on the other one. So we have nx minus my over m equals to m is y minus x, and nx is 0 and my is 1. So you get minus 1 over y minus x. You see already this is not a function of y because you have both x and y, right? However, how about this one? You have a constant. The constant function can be either a function of x or a function of y. So you can just consider this a function of x. This doesn't work, so you can use this one. So what's the integrating factor? You take an integration of 1 and then take an exponential. So mu is equals to e to the 1 times d. Now, because I take this 1 as a function of x, I have to take the integration by x. So this is e to the x. So it says e to the x is integrating factor. Let's multiply that to the equation. E to the x dx plus e to the x dy equals to 0. So this part is now m, and this part is n. You can check again whether this becomes the exact formula, but you can just believe that this will be an exact differential equation because we just follow the formula of the integrating factor. So we have to find our two-variable function satisfying the condition f of x equals to this y minus x, and f of y equals to e to the x, y minus x e to the x, and f of y equals to e to the x. So let's start from the simple one. So if you take the y derivative and you get e to the x, then you should have e to the x y plus, now in this case, some factor of function of x. Now, if you assume that this was your function, then what you should get by taking derivative of x is e to the x y plus g prime x, and that must be equal to this one, y e to the x minus x e to the x. So it says g prime x must be equals to minus x e to the x. So therefore, gx must be integral of x e to the x dx. So what's the integration here? So you have gx equals to minus of x e to the x minus and minus. So it's plus e to the x dx. So therefore, it's minus x e to the x plus e to the x. And also, you don't have to put a constant here. I keep emphasizing because later we're going to write your solution as f equals to another constant. So there's a redundancy, put a constant. Yeah, so solution is e to the x, y plus gx, x, e, x plus e, x equals to some constant. So this is a solution. This is the implicit solution. Or you can write it as an explicit solution in this case, because you can write your y in terms of x simply by taking all the factor of x to the right hand side. Get y equals to, in this case, c to the e to the minus x plus x minus 1, right? You can write your solution in explicit form if you want. Yeah. Okay. So I will take questions right now, and I'll do this the remaining part of the slide in the next lecture. So let me answer the question why the first equation cannot be solved by separation of variables. So why this one, the same equation, cannot be solved by separation of variable. So when you try to solve your equation by separation of variable, you need to have this type of formula, so f of x and g of y. You have the multiple of function of x and function of y. Or you should have a fraction of function of x and function of y. In that way, only you can take separate factors to each part, so that y part goes the left-hand side, for example, and x part goes to the right-hand side. Here, this is not a factor of x and y. This is simply a sum of x and y. You cannot separate by a factor of x and y. So another question is, so how do you distinguish which one is a function of x and which one is like a function of y? So first of all, you have to compute these two formulas. Okay. You don't have a situation when these two formulas satisfies these two conditions. Only either one of these conditions will be satisfied. So either this formula is function of x or this formula is function of y. So if you, in this example, if you compute it up to this far and you got 1, and you can safely assume that this is function of x at this point. But if you're not confident whether you can take this as a function of x, just compute another part, okay? Then you will always see that the other part will not satisfy the condition. So either this condition is satisfied or this condition is satisfied. Best way is just see both formula and see these conditions, two conditions, which one of these two conditions are satisfied. Okay, so I'm trying to keep, yes. No, so I'm not telling you that in any differential equation you will have one of these conditions satisfied. There are differential equations that none of these conditions will be satisfied. Then you cannot solve that differential equation by integrating factor. So if you can find, so I'm telling you that if you can find an integrating factor, then either one of these conditions will be satisfied. So if I'm telling you to solve some differential equation using integrating factor, then I'm assuming that you can solve this by the integrating factor. So you can check these two conditions, and you can easily see that only one of these two conditions will be satisfied. So if you get some condition, if you get some formula and you're not sure about, first formula is not telling you obviously that the condition is satisfied, then just look at the second formula and check the condition again. Then you will see which one is satisfying the conditions. So we don't know whether the first one will satisfy or second one satisfies. So you have to see the both. Okay, so any other questions? So it's 10:58.